Okay, today we're going to talk about the Hartley oscillator. So I'm going to use pictures from a book. It's called Solid State Electronics, Principles and Applications by Timothy J. Maloney. I've got many books on electronics, I gotta say, and I thought that this book explained the Hartley oscillator the best. So that's why I'm using his pictures. So in the art of the Hartley oscillator is of course an LC oscillator, which is also called a tank circuit. So it's just a capacitor in parallel with a inductor. So here I'm showing once the capacitor has been charged to 10 volts, what happens in the tank. So here I'm just showing this shows the voltage, the V top, and the current, the I, as time goes by. So you have two sine waves, and one V is in front of I by 90 degrees. I'm pretty sure you already know about all this, so I'm not gonna go too much into the details, but basically, if I look at here, the capacitor discharges into the inductor. I goes from 0 to max, and there is a magnetic field that's being created around the inductor. Okay, so you get to here, so I large, and you have a strong magnetic field, and the voltage is 0. So that's the first quadrant here. Okay, so V goes to 0 and I goes to its max. So I'm not going to explain the other moments, but what I'm going to do is that I'm gonna leave this here. That explains everything. I mean, it's pretty simple anyway, but I'm just gonna pause and just read that thing. Okay, but it's basic stuff. Okay, so let's move on. Of course, if you go back to here, so this is an unassisted tank circuit. So assuming that there's no resistance and everything is perfect, that's what you get. The amplitude doesn't change. In reality, of course, that doesn't happen. If you draw, what's gonna happen is that it's gonna go down. Okay, so it's gonna go to 0 if there's not a feedback of some sort, if there's no power going into the system. So okay, so you need something. Okay, so that brings us to Hartley. And Hartley, what it did is that he tapped the inductor, so splitting the voltage, the VC voltage, into two parts. So 80% is gonna go here, so the V top, 8 volts, and 20% of that voltage is gonna get here, so minus 2 volts. Okay, so this here is minus 2 volt, as explained here, same thing. And what it does is explained here very well. So the waveforms of VC, the total tank voltage, V top and V bot, so that's what this shows. So the voltage V bot is 180 degree out of phase with the others. So you have the VC, the capacitor voltage, varying from 10 to minus 10, V top 80% of that voltage, so it varies from 8 to minus 8, and the V bot takes 20% of the voltage and it varies from 2 to minus 2, and it's, as you can see, opposition phase. So when this one is maximum in the positive, this one in maximum is in the negative. Okay, so that's the idea of the Hartley oscillator. First you need to tap your inductor, and you ground the tap so that you have positive here and negative there. Okay, so that gives you the opposition, the phase opposition. The ground gives you the phase opposition. Okay, so next, what else do you need? You also need, okay, so what else do you need to keep the oscillation going? So you need to amplify the V-bot. You need to amplify the V-bot, yeah, so that it goes to at least 10. So let's look at that. Okay. So this is your tank, this is your tapped inductor, and the tap is at ground level for the voltage. So you have the V-top, V-bot, the VC is here. So the V-bot, what you do is that it becomes the input to an amplifier, and there's a coupling capacitor here that blocks the DC. So this thing here, this whole thing here, is a common emitter. It's a common emitter amplifier. Okay, so it's a common emitter amplifier. So what's going to happen is that V in is going to be amplified, and there's going to be another phase opposition between the V in and the V out. So that's the output here. So if you look at the, just a quick note about the common emitter amplifier. That's the basic circuit. So you have RB1, RB2 for the biasing. You have the collector resistance, and you have the emitter resistance, which is the reason why you have a resistance in the emitter lead is to stabilize the biases. That way, the behavior of the amplifier doesn't depend on the beta of the transistor. Okay, so you probably know this, but the voltage gain is it's roughly equal. Roughly equal to RC over RE. Okay, so it's not dependent on the beta. Okay, so let's move on. So let's look at the. Okay, so you have the V-top at the top of the tank, the V-bot at the bottom, and this is the V-out. So this is the output of the amplifier, where V-bot is the input. So as you can see, you have 180 phase difference between V-bot and the V-out. And what you want is for the V-out to be above the 10 volts, so that the oscillation can keep going. Okay, so V-out is 180 degree out of phase with V-bot, the input to the amplifier, which is also the bottom of the tank, of the LC tank. Okay, so now, we have seen that V-out is an amplification of V-bot. So now what happens is that you have to connect the V-out to the top of the LC tank circuit. Okay, so this is the same picture. This is the same picture as here, except that in this one, V-out here. This was V-out here. V-out is connected to V-top, and this is your final output here. Okay, so this is the only difference between what I just showed just a moment ago. the previous slide. Okay, so this is the tank circuit. You have the 80%, 20% tap. Tap is grounded. So this is the bottom of the tank, and this is the input. That's the input to the common emitter amplifier, and this is the output. And that output you connect it to the top of the LC tank. So okay, so what you have to be aware of. Okay, let me just. Okay, so let me first. We know that the voltage gain is about RE. Oh no, sorry, RC over RE. Okay, so that's your voltage gain, RC over RE. Here it's controlled by a potentiometer, so that you can change it. And what you want to do is that you want to make sure that the voltage gain is such that the transistor works as a class A amplifier, so that it's in its linear its linear state. You don't want to go into cutoff, you don't want to go into saturation, so you have to play with that pot in order for the voltage to be just above the 10 volts. Okay, so here this is like a schematic view of the whole thing. So you have the LC tank circuit. So this is the V-bot. It's the feedback. It's called the feedback, positive feedback. So this is 0.25 of V out. Okay, because we have that 80-20% split here. So this is the tap. So it's 80-20, so that's why you have a 0.25 here, a quarter. So you get the quarter of the output. So that's the sine wave. So this becomes the input to the amplifier. And here the AV is 4. So you would turn the pot so that you get an AV equal you would turn the pot so that AV is equal to 4. So that gives you this sine wave. So it's 4 times what came in, so you end up with V out. And this is what you see here. So what you do is that you turn your pot so that the amplifier is always in its linear state, and you want to make sure that the voltage that you get out from the amplifier is about 10 volts. In our case, 10 plus volts, but not too much. Don't go overboard. Don't go overboard, otherwise it's gonna go out of its linear state, and you're gonna get all kinds of distortion in your signal. Okay, so this is the schematics they use, or he uses in his book to explain, but in reality it's a little bit more complex, because usually so this is a common emitter here, the amplifier, common emitter, and this is a common base. Okay, so it's separated here. So this is common emitter. So what happens is that the LC tank circuit is directly connected to the it's in the collector lead. So this is the collector, this is the base, that's the emitter. So the LC tank circuit is in the collector lead directly. Other than that, it's the same thing. And here, instead of using the ground, is using a plus 12 volt, which doesn't matter, because you can use if you use a DC power here. I mean, for the AC signal, this behaves like a ground anyway. so you would have the same behavior. But always remember that the key to the Hartley oscillator is that you have a phase opposition because of the tap, so that you are 180 degrees out of phase. But the amplifier, the common emitter, it's gonna also induce a phase difference of 180. So at the end you have two 180 degree phase variation or difference, which means that at the end you have 360, which is 0. Okay, so that's the important part. The V in is in phase with the V out if you look at the whole thing. Okay, so that's the important part. Okay, so I think I'm going to stop here. So please like, comment, subscribe, and I will do more videos like this. Thank you for watching, and I'll see you around. Bye.